Hello, this is Mrs. Taylor, and I'm going to explain the concept of infinite limits. So the question is, how do I evaluate limits involving infinity? And there's two cases, one in which x is approaching positive or negative infinity, and then one in which the limit itself equals infinity. So first let's talk about the case where x is approaching an infinite amount. And an even smaller subset of that are the cases where there's a finite limit as x is approaching positive or negative infinity. So what that means is your x is approaching infinity, but the limit equals a value. It's finite. It's a set value. So the way it looks is on the left here we have the limit as x approaches infinity, and on the right, the limit as x approaches negative infinity. And in words, we're really trying to find what the limit of f is as x moves to the right when you're approaching positive infinity, and as x moves to the left when you're approaching negative infinity. So it's more of a question of end behavior. So let's consider the function f of x equals 1 over x. If we want to examine the limit, let me rewrite that. It's a bit messy. Let's try again. The limit as x approaches positive infinity of this function, which instead of writing f of x, let's just write 1 over x. What we're actually asking is, as 1 over x moves to the right through an infinite number, what is the end behavior? Is it approaching a set value? So if you think about it, if I have 1 over a very large number, 1 over a very large number is basically equivalent to 0, or it's at least approaching 0. And if you plug an even larger number in there, you're going to get an even closer value to 0. So if you just think through this limit, you can conclude that the limit as x approaches infinity of 1 over x is 0. So the end behavior is that this curve is going to approach 0. And then if I am examining the limit as x approaches negative infinity of 1 over x, now I'm trying to think about what's happening as the curve moves to the left through infinity, through negative infinity. And so if you think about it, I'm putting smaller and smaller, or smaller and smaller because it's negative, but larger and larger numbers in here, it's still approaching 0. Even though it's approaching negative infinity, 0 is 0. Positive and negative doesn't matter. So this limit would also be 0. If we look at it graphically, so 1 divided by x, you can see that as I'm approaching negative infinity, this curve is getting closer and closer to the x-axis. As I'm moving out to the right, approaching positive infinity, it's also getting closer and closer to the x-axis. So that would be y equals 0. So that is why this limit as x approaches infinity or negative infinity is both 0 in behavior as it moves to the left and to the right. So here's the formal definition. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x, either if the limit as x approaches infinity of f of x equals a value b, or the limit as x approaches negative infinity of f of x equals b. So we're taking exactly what we just did, an infinite limit, and we're giving it a name, horizontal asymptote, which you should have seen before now. So you may have some experience with this. Maybe not in limit notation, but you may have already identified asymptotes before. So the idea is that an asymptote is a limit as x approaches positive or negative infinity that equals a value. And so when you are asked to give the horizontal asymptote, your answer is y equals whatever that limit is equal to. So let's try this example down here. So the limit of ugly m, the limit as x approaches positive infinity of 2 plus 1 over x is, Well, we know the limit as x approaches infinity of 1 over x is 0. So this would be 2 plus 0, which is just 2. And then the limit as x approaches negative infinity of 2 plus 1 over x. And again, we have the scenario here that even though it's negative infinity, we're still approaching 0 as we move out to the left. So this would still be 2 plus 0, which would be 2. So if they're asking me to give horizontal asymptotes, what I would say is there is a horizontal, it's hard to write that in cursive, asymptote and its y equals 2, because that would be a horizontal line. So that would be how I would discover horizontal asymptotes using infinite limits. So let's look at one more example. In this case, this function, f of x equals x divided by the square root of x squared plus 1, a little more involved, a little bit more difficult to think through. Not impossible, but more challenging. So in this case, they want you to use graphs and tables to find that limit. So if we go to our calculator and clear out what we have, and we have x divided by the square root of x squared plus 1 and if we graph that, looks kind of like a stretched out S, and it looks like maybe it's leveling out as I move to the left at -1, and as I move out to the right at +1. And it, you know, the best way to really tell is to look at a table. So let's go to our table, and we want to start at, oh, I don't know, let's just start at 0. But this time we want to count by really large quantities because we're approaching infinity or negative infinity. So let's pick something really big. How about 1,000? Let's see what happens. Oh, change that back to auto, and then go to your table. And look, as it's getting infinitely larger, it is approaching 1. And as I move to the left, as it's getting infinitely smaller because we're going in the negative direction, but the number is still getting bigger, it's approaching -1. So I would say the limit as x approaches infinity of my function f of x equals 1, and the limit as x approaches negative infinity of the function equals -1. So this is a case where my positive and negative infinity limits are different, which we haven't seen yet. All right, last thing to keep in mind when doing these problems is the shortcut rules, okay? So there is a shortcut if you have a quotient, which means a rational, a fraction bar, involving polynomials. Okay, polynomials are expressions with multiple terms where you have like x squared plus x minus 3. And so the rule, and this may be where you've seen it before, asymptotes, horizontal asymptotes, is the limit as x approaches positive or negative infinity. If the degree of your polynomial on top is greater than the degree of your polynomial on bottom, will be infinity. Because think, if it's infinitely getting bigger on top than on bottom, that's going to be infinite. If the degree is on the bottom is greater than the degree on the top, that's the case we have with our first example, where the bottom of the fractions get infinitely bigger than the top, so we are approaching 0. And then if the degree on the bottom is equal to the degree on the top, this is where you have to do a little more work. You have to put the leading coefficient of the numerator over the leading coefficient of the denominator. And remember, your leading coefficient is the coefficient of the term that also determines your degree. Okay? One little detail that a lot of students struggle with is to keep in mind that degrees, you can estimate these limits using some loose rules on degrees. And what I mean by that is if I have the square root of x squared plus 1, we know that we can't just simplify this by taking the square root of each term individually. However, when you are trying to figure out the limit as x approaches positive or negative infinity, the degree of this type of expression would be whatever you get if you did simplify. So the square root of x squared would be x, so that degree would still be 1. So it's just a shortcut to get you through these infinite limits. Sometimes you are going to have to reason through it. Sometimes you're going to have to put in your calculator. Sometimes it's really nice and straightforward using these rules.